A caching-only DNS name server resolves queries on behalf of end devices and saves the results in a cache. A forwarding DNS name server forwards all queries to the caching-only name server and saves the result in a cache. To explain how to configure, test, and verify these name servers, I will use a pre-built RHCE practice lab. In this lab, I have 3 RHEL Linux systems. I will configure name servers on these 2 systems and use this reaming system for testing. I used VMware Workstation to set up this lab. It doesn't matter whether you use physical or virtual systems to set up the practice lab, the instructions and configuration steps for DNS name servers are the same. If you want to use physical systems to replicate this lab, you need 3 systems. You need 2 systems for server configurations and 1 for client configuration. You also need the internet connection. Connect systems with the network and note down the modem's IP address. Configure modem's IP address as the default gateway IP address. My modem's IP address is 192.168.29.1. Therefore, I will use this IP address as the gateway IP address on all virtual machines. Use an IP address from the gateway IP addresses network for each system. I will use the IP addresses 192.168.29.100/24, 192.168.29.101/24, and 192.168.29.102/24 for RHEL Server 1, RHEL Server 2, and RHEL Client. Configure the IP address 8.8.8.8 as the DNS server's IP address. If you know your ISP's DNS server's IP address, you can use that. If you do not know that, you can use this address. This IP address belongs to Google's public DNS server. Disable IPv6 configuration. To keep this tutorial simple, I will use only IPv4 addresses. The configuration steps for both IPv4 and IPv6 are the same. Access any website to verify the system can access the internet. Let's perform these steps in our virtual lab. I prepared this lab exclusively to explain RHCE exam topics. Since the RHCE exam does not allow candidates to use the internet, I did not configure this lab to use the internet. To perform the exercises explained in this video, we need to connect all virtual machines to the internet. To do this, we need to change the network connection type. Currently, the network connection type of all 3 systems is LAN. We need to change it to bridged. A bridged connection allows the virtual system to access the host's internet connection. To change the network connection type, power off the virtual machine, open its settings, and click the network adapter option. On the open window, select the network connection type to bridged. Repeat the same process on RHEL Server 2 to change the connection type to bridged. Verify the connection type is changed to bridged. Now, we need to change the connection type on RHEL Client. Open the network adapter's settings and change the connection type to bridged. Verify the updated connection type on all 3 systems. Now power on all virtual machines. Log in from the root account and update the IP configuration. To update and verify the IP configuration, we can use the NMTUI utility. It works on both CLI and GUI interfaces and provides a curses-based interface to manage interfaces. Open a terminal. Run the NMTUI command. Select the Edit a Connection option and press the Enter key. Open the Ethernet interfaces setting. Change the IPv4 configuration to manual. Assign the IP address 192.168.29.100. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IPv6 configuration. Save the connection. To apply the changes, we need to restart the interface. Select the Activate a Connection option and press the Enter key. To restart the interface, first, deactivate it and then activate it again. Quit the utility. To verify internet access, we can use the ping command. If you get replies, it verifies the system can access Google's website. On the GUI interface, we can also use a browser. Open Firefox and access any website to verify the internet access. On RHEL Server 2, we need to repeat the same process again. Log in from the root account. Run the nmtui command. Select the Edit a Connection option and press the Enter key. Open the Ethernet interfaces setting. Change the IP4 configuration to manual. Assign the IP address 192.168.29.101. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IP6 configuration. Save the connection. Restart the interface. For this, select the Activate a Connection option and press the Enter key. Select the connection and deactivate it. Activate it again. Quit the utility. To verify internet access, use the ping command. Repeat the same process on RHEL client. Log in from the root account. Run the nmtui command. Select the Edit a Connection option and press Enter key. Open the Ethernet interfaces setting. Change the IP4 configuration to manual. Assign the IP address 192.168.29.102. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IP6 configuration. Save the connection. Select the Activate a Connection option and press the Enter key. Select the connection and deactivate it. Activate it again. Quit the utility. To verify internet access, use the ping command. We also need to test connectivity between all three systems. Let's send ping requests to RHEL Server 1 and RHEL Server 2 to test connectivity. As we can see here, all three systems are connected and have internet access. The named service runs the DNS server. The bind package provides the named service. The bind utils package provides the tools we need to manage the named service. We need to install both packages on the system which we want to use as a DNS server. In this lab, we will use RHEL Server 1 and RHEL Server 2 as DNS servers. Therefore, we need to install these packages on these systems. RHEL Linux installs packages from repositories. When we install RHEL Linux, the installation process automatically configures the system to use RedHat's online repositories. To use these repositories, we need to purchase RedHat's subscription. If you have RedHat's active subscription and the system is connected to the internet, you can install packages from RedHat's online repositories. If you don't have RedHat's active subscription, you can configure a local repository from RHEL's installation disk and use it to install packages. To learn how to do this, you can check this video. Let's install both packages on both systems. To install packages, we use the DNF command. It supports many options and arguments for various functions. To install packages, it uses the install option. After the install option, we need to specify the package's name we want to install. If we want to install multiple packages, we can specify their names in a sequence. To separate package names, we use a single space between package names. To install the bind and bind utils packages, specify their names and press the Enter key. The command checks all specified packages on the system. If any package is already installed, it skips that package. It checks the dependencies of the remaining packages. If any package needs any additional packages, it automatically downloads them with the specified packages from the available repository. After downloading all packages, it calculates and prints the disk size they need, and asks the user to confirm the installation. To confirm the installation, we need to type the letter Y in lowercase and hit the Enter key. To cancel the installation, we need to type the letter N in uppercase and press the Enter key. Apart from the letters Y and N, all other letters are considered invalid input. For an invalid response, it prints the prompt again. To verify it, let's give an extra space after typing the letter Y and hit the Enter key. As we can see here, it is considered an invalid input. Type the letter Y again and press Enter key to confirm the installation. After confirmation, the command installs specified packages and prints the result. As we can see here, the package has been installed successfully. Repeat the same process on RHEL Server 2. Log in from the root account and installs the bind and bind utils package. Type the letter Y and press the Enter key to confirm the installation. As we can see here, the package has been installed successfully. Currently, the system is configured to use the ISP's default caching-only server or Google's public caching-only DNS server. Linux saves the caching-only DNS server's IP address in the /etc/resolve.conf file. To use a locally configured caching-only DNS server, we need to change this IP address. Start the NMTUI utility. Open the connection. We will configure the caching-only name server on this system. Therefore, we will use this system's IP address here. Save the connection. To apply the change, we need to restart the connection. When we restart the connection, the Network Manager updates all configuration files to use the new configuration. Quit the utility. Verify the change. Name.conf is the main configuration file of the DNS server. When we install the bind package, the installation process copies this file from the package to the /etc directory. By default, this file is configured to run the DNS service as a caching-only DNS server on the local system. With the default configuration, it accepts queries only from the local system. To accept queries from other computers, we need to configure this option. It defines the IP addresses on which the DNS server will listen for queries. We need to add this computer's IP address here. This option defines client computers from which this server will accept queries. By default, it accepts queries only from the local system. To allow this server to accept queries from the local network, we need to add the local network's network ID here. Save the file. Restart the named service. If the service restarts without any error, the service is ready to resolve queries. If the service does not start or you get any error, check the name.conf file again. A small mistake in this file can block the service from starting. Let's understand it through the example. Open the file again. Remove this semicolon and save the file. Restart the service. As we can see here, the service does not start this time. If you don't know why a service fails to start, you should start debugging process from the systemctl command. Use this command with the status option. With the status option, this command prints the current state of the service. If a service failed to start, it prints the step or line number in which the service failed. As we can see here, the service failed on line number 11 because we missed a semicolon before the closing curly bracket. Open the file again. Add the semicolon and save the file. Restart the service. As we can see here, the service starts again without any error. DNS clients send DNS queries on port 53. There are two protocols, TCP and UDP. After verifying the DNS service is running, we need to verify that port 53 is open on both protocols. To verify it, we can use the netstat command. This command shows the open TCP ports. As we can see here, the DNS service is listening for DNS queries on port 53. To view the opened UDP port, change this option to U. As we can see here, port 53 is open on the UDP protocol. We have configured this system as the caching-only DNS server. To verify it, we can use the host command. This command sends a recursive query to the configured DNS server. As we can see here, the query has been resolved by the caching-only DNS server configured on the local system. To verify, the caching-only DNS server stores the result in the cache and uses it to resolve the subsequent queries for the same name. Let's send one more query. Since it received a recursive query for this name the first time, it resolved the query from the authoritative DNS servers and saved the result in the cache. It took 994 milliseconds to resolve this query. Now send the same query again. Since this time, it already has the answer to this query in the cache, it resolved the query from the cache. This time it took only 25 milliseconds to resolve the query. Let's send the same query again. This time it took only 22 milliseconds. It verifies the caching-only DNS server resolves queries from the cache. It uses the authoritative DNS servers to resolve a query only if the answer to the query is not available in the cache. DNS provides a command line tool called RNDC for cache management. We can use this tool to view the cache data. DNS stores the cache data in an encrypted format. To view the cache data, first, we need to convert it into a regular text format. This command converts the cache data into regular text format and saves the output in the /var/name/data/cache_dump.db file. To find a particular record in the cache data, we can use the grep command. For example, this command finds all records related to the name google.com. The caching-only DNS server saves only the answers it receives from the authoritative name servers. It means you will find records only for the names that have been resolved by the caching-only DNS server. To verify it, let's find the name yahoo.com. Since we did not send any query for the name yahoo.com, there is no cache data for this name. Let's send a query for this name. Dump the cache data again and find the records related to this name. As we can see here, this time the cache has records for this name. It verifies the caching-only name server saves results in the cache and uses them for subsequent queries. Let's send one more query for the name yahoo.com and compare the time it takes to resolve. This time, it resolved the query from the cache and took 0 milliseconds. When it resolved the query from the authoritative DNS servers, it took 1 millisecond. It verifies a caching-only server increases DNS performance and reduces network loads by obtaining a single copy of frequently accessed information and making it available many times with no additional overhead. Now, let's test the caching-only DNS server from the DNS client computer. To configure a DNS client, we need to update its DNS server's IP address. Start the NMTUI utility. Edit the connection to update its DNS server's IP address. We configured the caching-only DNS server on the RHEL server 1. Therefore, we will configure RHEL server 1's IP address here. Save the configuration. To apply the new configuration, we need to restart the connection. As mentioned earlier, Linux saves the DNS server's IP address in the /etc/resolve.conf file. We can check this file to confirm the DNS server's IP address has been updated. As we can see here, the system has been updated to use the local caching-only DNS server. Let's use the host command to send a DNS query to it. As we can see here, the client fails to reach the configured DNS server. Now, let's run the same command on RHEL server 1. As we can see here, RHEL server 1 can reach the configured DNS server. Can you guess why RHEL server 1 can reach and RHEL client cannot reach the configured DNS server while the configured DNS server is the same for both systems? The answer to this question is the default firewall. All RHEL Linux systems have a default firewall that does not allow other computers to access the services running on them. If you want to make a service publicly accessible, you have to configure the firewall to allow that service. The default firewall divides traffic into zones. By default, it enables the default zone. If you did not change the default zone, you need to DNS service in the allowed services of this zone. If you have changed or configured the other zone, you need to add the DNS server in that zone. This command prints the default zone's name. This command adds the DNS service in the allowed services of the default zone. It adds the service in the current session only. In the next session, you need to run this command again. If you want to add the DNS service permanently, use the permanent option. Now test from DNS client again. As we can see here, now the client can access the caching-only DNS server configured on RHEL server 1. Let's perform a few more tests. For each recursive query, the caching-only name server checks the cache. If the answer to the query is available in the cache, it provides the answer. If the answer to the query is not available in the cache, it communicates with the configured authoritative DNS servers, gets the answer, saves the answer in the cache, and provides the answer to the requester system. To verify it, we can check the cache data on the caching-only name server. Dump the cache data and search record for any query we sent from our HEL client. To delete the cache data, we use the flush option with the rndc command. Let's delete the cache data. To verify it, we can search for any previously resolved names. As we can see here, the cache data has been removed. A DNS forwarder is a resolver system that forwards all queries to the configured caching-only DNS server. Forwarding DNS queries to a caching-only server is called DNS forwarding. A DNS forwarder is similar to a caching-only name server. If we have a caching-only name server, we can easily convert it into a DNS forwarder. In our lab, we have configured and verified the caching-only name server on RHEL Server 1. We will convert it into a DNS forwarder. Since a DNS forwarder forwards queries to a caching-only name server, we also need a caching-only name server. We will configure RHEL Server 2 as the caching-only name server. To convert a caching-only name server into a DNS forwarder, we need to configure the two options, forwarders and forward only in the /etc/name.conf file. The forwarders option requires the IP address of the caching-only name server that will receive DNS queries from this system. In simple words, this system will forward DNS queries to the caching-only name servers configured in this option. In our lab, we will configure the caching-only DNS server on RHEL Server 2. RHEL Server 2's IP address is 192.168.29.101. Therefore, we will add this IP address to this option. A DNS forwarder forwards DNS queries to the configured caching-only name server. If DNS queries fail because of a server error or timeout, a forwarder starts working as the caching-only name server. When it receives a recursive query, it forwards the query to the configured caching-only DNS server. If it receives the answer to the query, it saves the answer in the cache and provides the answer to the requester. If it does not receive the answer to the query or the configured caching-only DNS server is down, it directly communicates with the authoritative DNS servers and resolves the query. In simple words, if the configured caching-only server is up, it works as a DNS forwarder. If the configured caching-only DNS server is down, it works as a caching-only DNS server. This is the default behavior of a DNS forwarder. The forward-only option overrides this behavior and configures the name server as a DNS forwarder-only server. If we configure this option, the system works as a DNS forwarder only. If the configured caching-only DNS server is down, it does not resolve the query itself. But it can use its cache to answer the query. So if the answer to the query is already available in the cache, the client will get the answer to the query even if the configured caching-only DNS server is down. Let's understand it through an example. Suppose a client sends a query to resolve the name yahoo.com to a DNS forwarder-only system. The system checks its cache to find the DNS records related to the name yahoo.com. If it finds the records, it provides them to the requester system. If it does not find the records, it forwards the query to the configured caching-only DNS server. The caching-only DNS server resolves the query and replies to the DNS forwarder system. The forwarder system saves the answer in the cache and replies to the requester client. Now suppose, the configured caching-only DNS server is down and another client sends a query to resolve the name yahoo.com to the DNS forwarder-only system. Since the answer to the query is available in the cache, the system replies from the cache. It does not forward the query to the configured caching-only DNS server. This way, even if the caching-only DNS server is down, the DNS forwarder system can resolve queries from its cache. But it will resolve only queries whose answers are available in the cache. If a query's answer is not available in the cache, it will not resolve the query. For example, a client sends a query to resolve the name Amazon.com to a DNS forwarder-only system. If the answer to this query is not available in the DNS forwarder-only system's cache and the configured caching-only DNS server is down, the client will get an error message indicating the host is not reachable. Configure both options and save the file. Flush the cache data. Restart the name service. Now, this system has been configured as a DNS forwarder only. It will forward all queries to the configured caching-only DNS server. Let's configure RHEL Server 2 as the caching-only DNS server for the DNS forwarder system. Open the /etc/name.conf file. Add this system's IP address in this option. Add DNS client's network ID in this option. Save the file. Currently, this system is configured to use Google's DNS server. Open the IP configuration and update the DNS server's IP address. We will configure the caching-only DNS server on this system. To configure this system to use the locally configured caching-only DNS server, we need to change this IP address. Save the configuration. Restart the connection to apply the change. Restart the name service. Verify the system is configured to use the locally configured caching-only DNS server. Send a recursive query to test the configured caching-only DNS server. As we can see here, the query has been resolved successfully. It verifies the caching-only DNS server is working properly. Verify port 53 is open on both protocols. Add a allow rule for the DNS service in the default zone of the firewall. If we don't add this rule, DNS client systems cannot access the caching-only DNS server configured on this system. If you want to add this rule permanently, you can use the permanent option. Before we test this server configuration from the DNS client system, let's verify the server is caching the records. For this, dump the cache data. Search records for any previously sent query. As we can see here, the server is properly caching the records. Now, let's flush the cache to perform new tests. To test and verify the DNS forwarder-only configuration, check the cache data on RHEL Server 1. Since we have already flushed the cache data, there must be no data in the cache. As we can see here, the cache is empty. Now send a recursive query from the client system to it. As we can see here, the query has been resolved successfully. Let's understand how this query was resolved. RHEL client, which is configured as a DNS client system, sent this query to RHEL Server 1. RHEL Server 1 is configured as a DNS forwarder only. It checked its cache and found no answer to this query. Since the answer to the query was not available in the cache, it forwarded the query to the RHEL Server 2. RHEL Server 2 is configured as a caching-only DNS server. It resolved the query, cached the answer, and replied to the RHEL Server 1. RHEL Server 1 did the same thing. It cached the answer and replied to the RHEL client. To verify it, let's check the cache data on RHEL Server 1 and RHEL Server 2. Remember, we flushed the cache data on both systems before performing this test. So, if we see any cache data on both systems, it must be generated because of the query we sent in this test. As we can see here, the answer to the query has been cached on the DNS forwarder-only system. Now let's check on the caching-only DNS server. As we can see here, the answer to the query has been cached on the caching-only DNS server as well. Now let's verify the fact that says, if the forwarder system resolves queries from the cache even if the caching-only DNS server is down. For this, ping yahoo.com. Since at this time, both the caching-only and forwarder systems are up, the yahoo.com will be translated from the caching-only server and the answer will be saved on both systems. Now stop the name service on the caching-only DNS server. Send ping request to msn.com. Since the answer to this name is not available in the forwarder system's cache and the caching-only DNS server is down, it must fail. Now ping google.com. The answer to this name is available in the forwarder system's cache. Therefore, it should be translated. Now send another request to amazon.com. It should fail. These tests verify the forwarder system uses its cache to answer the queries. Now start the name service on the caching-only DNS server and test again. As we can see here, the queries have been resolved. It verifies the setup in which the forwarder-only DNS server forwards and the caching-only DNS server resolves the queries. Now, open the /etc/namedconf file and configure this system as a primary name server for the example.com domain. Currently, this system is configured as a forwarding-only DNS server. These two options configure this system as a forwarding-only DNS server. First, we need to remove these options. These options are not part of the default configuration. I added these options to configure this system as a forwarding-only DNS server. If you are editing this file for the first time, you will not see these options. We need to configure these two options. Configure this system's IP address here. This option configures this system to listen for DNS queries on the IP address 192.168.29.100. Add the local network's network ID here. This option configures the network whose hosts can send DNS queries to this server. Collectively, these options configure this system to listen and answer DNS queries from the network 192.168.29.0/24 on the IP address 192.168.29.100. To resolve queries, it uses the zone section. To configure this system as a primary or master DNS server for the domain example.com, we need to add a zone configuration in the zone section. A zone configuration starts with the zone keyword. After this, we need to specify the domain name. All zone configuration goes inside curly brackets and ends with a semicolon. Inside the curly brackets, we need to configure three options: type, file, and allow transfer. The type option defines the role of this server for this zone. To configure this server as the primary or master name server for this zone, we use the value master here. To configure this server as the secondary or slave name server for this zone, we use the value slave here. The file option defines the name of the zone file. The name server uses this file to answer DNS queries that belong to this domain. By default, the name server looks for this file in the /var/name directory. On the primary or master name server, we need to manually create this file in this directory. The allow transfer option defines the secondary or slave name server's IP addresses. The name server automatically transfers zone files to name servers defined in this option. If we don't want this name server to transfer zone files to any other name server, we need to specify the value none here. We will configure this option later when we will configure a slave name server. Save the file. Since we configured this system as the primary authoritative name server for the domain example.com, we need to create a zone file for this domain in the /var/name directory. This directory contains a zone file for localhost. We can use this file as a template to create the zone file. Since it is an important configuration file, we will not use this template. We will create this file from scratch after understanding its configuration. DNS saves its database in zone files. A zone file stores records of a particular domain in simple text format. A zone file stores resource records in lines. For each record, it uses a separate line. If you want to create a resource record in multiple lines, you must use parentheses. DNS process everything you put between an opening parenthesis and a closing parenthesis as a part of the line. Administrators use this feature to make the start of authority record more human readable. This is a start of authority record. We will talk about this record later in this video. When processing, DNS removes these parentheses and arranges these fields in the same line. DNS looks at this record like this. To separate two fields in a record, you can use either spaces or tabs. Generally, tabs are used for it. Tabs provide a more attractive layout and clearly indicate the added and missed fields. This file uses spaces to separate fields. This file uses tabs to separate fields. As we can see here, if we use tabs to separate the fields in the records, the fields look neat and descriptive. We can easily identify which fields have values and which fields are empty. A zone file contains three types of entries: comments, directives, and resource records. A comment starts with a semicolon and continues to the end of the line. You can add a comment to any directive or record. DNS ignores everything you write after a semicolon till the next line. If you put a semicolon at the beginning of a line, DNS ignores the entire line. If you put a semicolon in the middle of the line, DNS ignores everything that comes after the semicolon. This is how DNS looks at this file. A directive starts with a $sign. It works as a variable. It stores value. DNS replaces a directive with its value when it processes the zone file. There are two important directives: TTL and origin. This directive is mandatory. It defines a default time to live value for resource records. All resource records have this field. If you want to define a specific time to live value for a record, you can configure its TTL field. If you want to use the default time to live value for a record, you need to leave the record's TTL field empty. When processing records, DNS uses the default time to live value in all blank TTL fields. DNS service includes this value with each record it serves from this file. Other DNS servers and resolver systems that receive a record served from this file use this value to cache the record. For example, if the time to live value of a record is 1 day, resolver systems and other DNS servers can cache the record for 1 day. After that, they must have to retrieve the same record again. By default, this directive accepts value in seconds. If you want to specify the time in other formats, you need to use related keywords. These keywords are M for minutes, H for hours, D for days, and W for weeks. The following examples set this directive's value to 2 days in different formats. You can use whatever format you like. In the DNS database, a resource's name can be either a fully qualified domain name or a relative name. A fully qualified domain name is a complete name. It includes the names of all top-level domains till the root domain. It ends with a dot. You can access a resource from anywhere in the domain system using its fully qualified domain name. This is an example of a fully qualified domain name. A relative name is a host name. It may or may not include the parent domain's name. It does not end with a dot. In the DNS system, you cannot access a resource from outside the domain using its relative name. However, you can access a resource inside the domain using its relative name. These are examples of relative names. You can use both types of names in the zone file, but DNS will process only fully qualified domain names. If you use a relative name in the zone file, DNS automatically converts it into the fully qualified domain name before processing it. To convert a relative name into the fully qualified domain name, it uses the origin directive's value. The origin directive stores the fully qualified domain name of the domain. It attaches the domain's fully qualified domain name to the relative name as a suffix to make it the fully qualified domain name. In a zone file, you can specify a name in 4 ways. You can specify a fully qualified domain name, a relative name, a singlet symbol, and a blank space. If you use a fully qualified domain name, DNS uses the name as it is. A fully qualified domain name always ends with a dot. DNS uses this rule to identify fully qualified domain names in the zone file. If a name ends with a dot, it assumes the name is a fully qualified domain name and processes the name as it is. In this zone file, these names end with a dot. DNS will process these names as fully qualified domain names. If a name does not end with a dot, it assumes the name is a relative name and converts it into the fully qualified domain name. To convert a relative name into the fully qualified domain name, it uses the origin directive's value. It attaches the origin directive's value as a suffix to the relative name. In this zone file, these names do not end with a dot. DNS will process these names as relative names. It will use the origin directive's value to convert these names into fully qualified domain names. If you use a singlet symbol in the name field, DNS replaces this symbol with the origin directive's value. For example, this resource record has an @ symbol in the name field. When processing this file, DNS will replace this symbol with the origin directive's value. If you use a blank space or leave the name field empty, DNS uses the previous record's name field's value. If we talk about this file, DNS will use the value example.com in the name field of these records. Let's understand how DNS will process the name fields of these records. This record has the @ symbol in the name field. DNS replaces the @ symbol with the value configured in the origin directive. This record's name field is empty. Because of this, DNS will use the previous record's name field's value here. By following the same rule, this record will inherit the name field's value from this record. The same thing will happen here and here. A resource record defines the characteristics and properties of an entity within the domain. There are many types of resource records. The main resource record types are start of authority, name server, mail exchanger, quad A, and PTR. Let's understand the meaning of each record in detail. The start of authority record defines the authoritative name server for the domain and configures its properties and characteristics. Since each domain needs a unique zone file, we cannot add more than one start of authority record in a zone file. We can add only one start of authority record in a zone file. It uses the following syntax. Let us understand this syntax field by field. This field specifies the domain or zone name. The name server whose name we specify in the name server field becomes the authoritative name server for the domain or zone whose name we specify in this field. Since we used an @ symbol here, it will be replaced by the origin directive's value. This field defines the time for which other name servers or resolver systems can cache this record. If we leave this field empty, DNS uses the default value defined in the time to live directive. This field defines the class type of this record. There are three classes: in, ch, and hs. Currently, only the in class is used. The ch and hs classes were used when the Internet was an in-house project in the MIT lab. Ch stands for chaos. It is an MIT LAN protocol. HS stands for Hesiod. It is an information service used at MIT. In stands for the Internet that we use today. Currently, only the in class is used. Ch and hs classes are used in special cases for specific reasons. This field defines the type of record. This field defines the authorized name server for this domain. It only defines the authorized name server for the domain. It does not map an IP address with it. To map an IP address with the authorized name server, we also need to create a host record for it. This field defines the administrative email address of the domain. You can use any valid email address in this field. Generally, administrators use the email address hostmaster here. It describes the purpose of this field. In other configuration files, the @ symbol is used as the separator in the email address. In a zone file, the @ symbol has a special meaning. DNS replaces the @ symbol with the origin directive's value. If we specify the email address hostmaster@theRateExample.com, DNS will read it as hostmaster.example.com.example.com. To avoid this confusion, DNS uses the dot separator here. In this record, I use the email address hostmaster.example.com as the administrative email address. DNS will read this address as hostmaster@theRateExample.com. These fields control the zone transfer process. Before we understand these fields, let's understand what a zone transfer is and how it works. A zone transfer is a process in which a master nameserver transfers zone files to the slave nameserver. As we know, in the DNS system, we can create zone files only on the master nameserver. The master name server automatically transfers zone files to the slave name servers when it receives zone transfer requests. The slave name server periodically sends zone transfer requests to the master name server. The slave name server uses these fields to define and control the frequency of the zone transfer requests. There are two types of zone requests: the complete zone transfer request and the start of authority record transfer request. The slave name server uses both types to speed up and optimize the zone transfer process. The first time, it makes the complete zone transfer request. The master name server transfers the zone file. The slave name server saves the received zone file. The next time, instead of making the complete zone transfer request, the slave name server makes the start of authority record transfer request. The master name server transfers the start of authority record. The slave name server compares the received start of authority record serial number with the locally saved zone file start of authority record serial number. If both numbers are the same, it assumes that the master name server's zone file is not changed. It keeps using the locally saved zone file. If both numbers are different, it thinks that the master name server's zone file has been changed. It sends a complete zone transfer request to the master name server. The master name server transfers the updated zone file. The slave replaces the locally saved zone file with the received zone file. This way, after the first time, a slave name server makes a complete zone transfer request only when the master name server's zone file changes. It uses the start of authority record serial number to detect changes in the master name server's zone file. Since the slave name server uses this number to detect changes, you need to update this number every time you make a change to this file. There is no predefined rule for this number. You can use any number from this range. Usually, administrators use the current date in the YYMMDD format and an incremental sequence number from the range 0 to 99 to generate a unique and updated serial number for every change they make in the file. For example, if we expend this serial number using this technique, we get these values. These values show this file was last updated on June 25, 2023. A 00 in the sequence field shows that this file was updated only once on June 25, 2023. If administrators update a zone file more than once per day, they can use incremental sequence numbers for every update. For example, this serial number shows the file was updated 3 times on June 25, 2023. The refresh time field sets the refresh time. The slave name server uses this time to determine how quickly it should check the master name server for an update. In this zone file, this time is set to 12 hours. Because of this, the slave name server checks for an update every 12 hours. If it gets an update, it asks for the next update after 12 hours. For example, the slave name server tries to reach the master name server at 12 a.m. If it connects, it will try again at 12 p.m. But if it fails, it will try again after the retry time. The retry time field defines the retry interval. If the slave name server fails to connect with the master name server, it can try again after this time. For example, in this zone file, this time is configured to 15 minutes. Because of this, the slave name server will try again every 15 minutes if it fails to connect to the master name server in a refresh cycle. It will keep trying until the expiry time. In this example, the expiry time is 3 weeks. Therefore, it will try to connect the master name server every 15 minutes until 3 weeks. For example, if it first tries on 12 a.m. of July 1, 2023, then it will try till 12 a.m. on July 22, 2023. If it succeeds on any try, it resets the refresh and retry times. If it fails to contact the master server till the expiry is reached, it stops working as a slave name server for the zone. After this time, it will not resolve queries for the domain. A slave name server resolves queries for the zone when the master name server is down. It resolves queries for the domain until the master is up or the expiry is reached. After the expiry, it does not resolve queries for the domain. At this point, since both the master name server and the slave name server are not resolving queries, the zone is considered dead. Resolver systems use the negative cache value to store negative responses. This value applies to all records served from this zone file. DNS provides this value in each answer. Let's take an example. Suppose, a resolver system asks this name server to resolve the name xyz.example.com. The server checks its zone file and finds no entry for the name xyz.example.com. It returns an error indicating the requested name does not exist and can't be resolved. It also includes the negative cache TTL field's value in the error message. The resolver system saves the answer in the cache and does not send a query to resolve the same name again until the negative cache time expires. In this example, the resolver system will not send a query to resolve the name xyz.example.com in the next 2 hours, starting from the time it received the response. For example, if it receives a negative response at 2 p.m., it will not retry until 4 p.m. for the same name. There are 2 types of name server records, authoritative and referral. An authoritative name server record authorizes a name server to resolve queries. A referral name server record diverts queries to the authoritative name server. Each authoritative name server needs both types of name server records. It requires an authoritative name server record in the domain zone file for which it resolves queries and a referral name server record in the parent domain zone file that forwards queries to this domain. Resolver systems can access an authoritative name server through referral name servers. DNS system organizes authoritative name servers in a hierarchy. Each authoritative name server resolves queries for its domain and provides a referral for the child domain. When an authoritative name server receives a query, it checks whether the query belongs to it or its child domain. If the query does not belong to it or its child, it returns an error indicating the requested host or service is not available. If the query belongs to it, it resolves the query. If the query belongs to its child domain, it provides a referral to the child domain's name server. It only provides referrals for its child domains. It knows nothing about its grandchild domains. If its child domain has child domains, the child domain will be responsible for providing referrals to its child domains. We need to create authoritative name server records in the domain's zone file. For example, if we want to create name server records for the example domain, we need to add authoritative name server records in the example domain's zone file. The name server record uses the following syntax. This field defines the maximum time resolver systems can cache this record. If we leave this field blank, DNS uses the default value of the TTL directive. This field defines the class type. This field defines the record type. The domain name field defines the domain for which it configures the authorized name server. If we leave this field empty, DNS uses the previous record's name field's value in this field. Usually, NS records are placed just after the start of authority record. Therefore, If we keep this field empty, DNS picks the start of authority record's name field's value as the default value for this field. In the start of authority record, administrators usually use a single @ sign in the name field. DNS replaces the @ sign with the value of the origin directive. With this setup, the start of authority record automatically receives the domain name from the origin directive, and NS records receive it from the start of authority record. In our example, we configured the domain name example.com in the origin directive. From this directive, DNS will automatically configure the domain name field of the start of authority record and NS records. The authorized name server field defines the authorized name server for the domain we configure in the domain name field. This record configures the name server ns1.example.com as the authoritative name server for the domain example.com. If the authoritative name server is available within the domain, we also need to create a host record for it. A host record maps a service or a host to an IP address. As I mentioned earlier, a resolver system can access a name server only from its parent domain. Because of this, we need to create an NS record for each name server in its parent domain's zone file. An NS record that we create in the parent domain's zone file is known as a referral name server record or a glue name server record. It sticks the child domain's name servers with the parent domain's name server. It uses the same syntax the authoritative name server record uses. The only difference between a referral or glue nameserver's record and an authoritative nameserver's record is that in the referral nameserver record, we use the domain name for which we are creating the referral in the domain name field. For example, if we want to create a referral name server record for the XYZ domain, we will use the XYZ domain's fully qualified domain name here. Since the referred domain is a child domain of this domain, we must have to create a host record for it also. If we create a glue record without the host record for the child domain's name server, the resolver systems cannot access the child domain's name server. Let us take an example to understand it. A resolver system wants to resolve the name ftp.xyz.example.com. By default, resolver systems only know the IP addresses of root nameservers. They save them statically in library files. For example, Linux saves root nameservers' IP addresses in the /var/name/name.ca file. The resolver system sends the query to the nearest root nameserver. The root nameserver provides a referral to the COM nameserver. The referral includes the COM nameserver's IP address. From the referral, the resolver system learns the COM nameserver's IP address and sends the same query to the COM nameserver. The COM nameserver provides a referral to the example nameserver. The referral includes the example nameserver's IP address. From the referral, the resolver system learns the example nameserver's IP address and sends the same query to the example nameserver. The example nameserver provides a referral to the XYZ nameserver. Since the query belongs to the XYZ nameserver, it resolves the query. Now, let us suppose the administrator forgets to add the IP address in the glue record of xyz.example.com in the zone file of example.com. In this situation, the example nameserver will provide a referral to the XYZ nameserver without its IP address. Since the resolver system does not know the IP address of the XYZ nameserver, it has to resolve this name first. To resolve this name, it follows the same steps. Since the resolver system can get the XYZ nameserver's IP address only from the example nameserver and the example nameserver does not provide it, the resolver system will keep repeating this process. It creates an infinite loop of queries between the resolver system and the example nameserver. To avoid this situation, you should always add a host record for the referral nameserver in the parent domain nameserver's zone file. DNS is an essential service. You should configure at least 2 nameservers for each domain. You should configure the primary name server within the domain. You should configure the secondary name server outside the domain in a different geographical location. This setup allows resolver systems to access resources even if the primary name server fails. We use the same syntax to add an NS record for the backup name server. If the backup name server is available within the domain, we also need to add a host record for it. If the backup name server is available outside the domain, we do not need to add a host record for that. As mentioned earlier, in a DNS system, only authoritative name servers can resolve queries. Because of this, we also need to configure the backup name server as the authoritative name server for the domain. If we do not do this, a situation called lame delegation occurs. A lame delegation occurs when an NS record points to a name server that is not authorized to answer for the domain. In this example, we configured a backup name server, ns1.example.net. We need to configure this name server as the authoritative name server for the domain example.com. To authorize this name server for the example domain, we need to configure this name server as the slave name server for this domain. A name server can act as a primary name server for one domain and a backup name server for another domain at the same time. This flexibility allows administrators to use existing name servers to configure backup name servers for other name servers. Let's take an example. Suppose we have two primary name servers ns1.example.com and ns1.example.net for the domains example.com and example.net. We can configure the ns1.example.com name server as the backup name server for the ns1.example.net name server and the ns1.example.net name server as the backup name server for the ns1.example.com name server. This setup allows us to configure backup name servers without adding any additional name servers to the network. MX records define mail servers. It uses this syntax. The domain name field defines the domain for which this record will define the mail server. Similar to an NS record, if we leave this field empty, the record will inherit its value from the previous record's name field. The TTL field defines the maximum time resolver systems can cache this record. If we leave this field empty, the record uses the TTL directive's value. In this example zone file, we have two MX records. In the first record, we define this field's value. In the second record, we left this field empty. Because of this, the first record will use the defined value. The second record will use the TTL directive's value. The class field defines the class of the record. The resource type field defines the record type. The preference field defines the priority of mail servers. If you configure multiple mail servers, you can use this field to define the order in which they should be used. You can use any value between 0 and 96,535. In order, a lower value has higher priority than a higher value. Typically, administrators use values in multiples of 10. They use the value 10 for the most preferred mail server, 20 for the second most preferred mail server, and so on. This method allows them to add additional MX records without changing the existing order. In this example, we use this field to configure the mail server mail.example.com as the main mail server and the mail server mail.example.net as the backup mail server. To define mail.example.com as the main mail server, we use the value 10, which is the lowest in the configured priority order. We used value 20 for mail.example.net to define it as the backup mail server. The mail server field defines the email server for the domain we configure in the domain name field. In this example, we configured two mail servers mail.example.com and mail.example.net for the domain example.com. We configured mail.example.com as the primary mail server and mail.example.net as the backup mail server. Our primary mail server is available within the domain. Our backup mail server is available in the external domain. With this configuration, if the primary mail server fails, the backup mail server will receive mail for the domain and forward them to the primary mail server as soon as it will come online again. If the mail server is available within the domain, we also need to add a host record for it. For example, this mail server is available inside the domain. Therefore, we need to add a host record for it. If the mail server is available outside the domain, we do not need to add a host record for that in the zone file of this domain. We need to add a host record for it in the zone file of that domain. In our example, we do not need to add a host record for mail.example.net in the zone file of the example.com domain. We need to add a host record for mail.example.net in the zone file of the example.net domain. We need to create host records of all resources available within the domain in the domain's zone file. If a resource is available in the external, parent, and child domains, we don't need to add that resource's host record in the domain's zone file. There is only one exception to this rule. We need to add a host record for the child domain's nameserver record. In this domain tree, we have 3 domains in one branch and 2 domains in another branch. The example domain is the parent of the XYZ domain and child of the CALM domain. We need to create host records for these resources in the zone file of this domain. We will create host records for these resources in the zone file of this domain. Same way, for these resources, we will create host records in the zone file of this domain. Since the XYZ domain is the child domain of the example domain, we need to create a host record for the XYZ domain's nameserver in the example domain's zone file. Similarly, we need to create host records for all nameservers in their parent domain's zone files. Besides nameserver records, we don't need to add host records of any domain in its parent domain's zone file. To add a host record, we use the following syntax. The name field defines the name of the host or service whose IP address we want to make publicly accessible. If we use a relative name here, DNS automatically converts it into a fully qualified domain name by adding the origin directive's value to it. The TTL field defines how long other name servers and resolver systems can cache this record. The class field defines the class type of this record. The resource record type field defines the type of record. The A record maps an IP4 address with the name of a host or a service. The quad A record maps an IP6 address with the name of a host or a service. The IP address field defines the IP address we want to map with the name defined in the name field. We can map multiple IP addresses with the same name. This feature is used when we run the same service on multiple hosts. If the same service is available on multiple hosts, we need to map their IP addresses with the service name. For example, if we configure the same web service on 3 hosts for backup and redundancy purposes, we need to map all 3 hosts' IP addresses with the service name. If we map multiple IP addresses with the same name, DNS provides an IP address for the name in a round-robin or random order. You can define this order by configuration directives. We can also map multiple names with a single IP address. You can use this feature when you run more than one service on the same host. For example, if you have a small website and use only a few email addresses for management and communication purposes, you can run the mail, web, and FTP services on the same server. This setup allows you to save the cost of additional servers. Let us understand this feature through our example. Suppose we configure the mail, web, and FTP services on a single server whose IP address is 192.168.0.2. In this situation, we need to map these services with the IP address 192.168.0.2. The CNAME resource record type assigns an alias name to the name of an existing host or a service. The alias name field defines the name you want to use for the existing name defined in the canonical name field. The canonical name field defines the actual name which you want to access by an alias name defined in the alias name field. This record type is used when you want to access a service from another name or hide your internal network structure from external users. Let's understand it through our example. Suppose we run the web service on a host called my web server. In this situation, we can map the name www with the name my web server. After this, DNS will translate the name www into the IP address of my web server. Users will access the web service running on the IP address of my web server by using the name www. Usually, administrators configure a web server to serve websites with and without the www. This setup needs a CNAME record in the zone file for the web service. To achieve this goal, you need to add a host record for the domain name and then you need to configure the www as the alias name for the domain name. A zone file only translates names into IP addresses. It does not run or provide any other service. If you add an alias name for a service, you also need to configure that service to respond to both canonical and alias names. In this example, you also need to configure the web server to respond on both names www.example.com and example.com. Since we configured this system as the primary name server for the example domain, we need to create a forward lookup zone file on this system. Create a forward lookup zone file and open it for editing. Use the same name for the file you used in the zone configuration directive. Although comments are optional, you should use them. They explain the meanings of directives and configuration settings. Create the time to live configuration directive. Set its default value to 2 days. DNS will automatically use this value in all empty TTL fields. Create the origin directive. Configure the domain name as its value. DNS will use it to convert relative names into fully qualified domain names. Create a start of authority record. This record is compulsory. We can create only one start of authority record in a zone file. This record defines the domain's properties and authority name server for the domain. Use parenthesis to define zone transfer specific options in multiple lines. Add a comment with each option to explain its meaning. Create name server records. First, create a name server record for the primary name server. If the domain has a backup name server, add a name server record for the backup name server. After name server records, create mail exchanger records. Add an MX record for the primary mail server. If the domain has a backup mail server, add an MX record for the backup mail server. Finally, add host records for all services and hosts that are available inside the domain. If the backup name server and mail server are available inside the domain, add host records for them. If they are available outside the domain, do not add host records for them in this zone file. Add some host records for testing. These hosts do not need to exist on the network. You can create any resource records for testing. Save the file. We can use the cat command to view and verify the zone file's contents. The default firewall configuration does not allow this system to accept DNS queries from other systems. The default firewall configuration will block all incoming DNS traffic. Add a rule in the firewall to allow incoming DNS traffic. DNS will not read the new zone files until we restart the named service. Restart the named service. To verify the configuration, we can use the host command. This command uses the configured name server to translate the specified host name. The output of this command verifies the locally configured name server is translating names correctly. We can also use the dig command. This command sends name resolution queries to the configured DNS server and displays the response. As we can see here, it received this response from the name server configured on this system. Now, let's verify this configuration from the DNS client system. To verify this system is configured as a DNS client, we can check the resolve.conf file. Use the dig command to send a DNS query to the configured name server. As we can see here, the name server is resolving DNS queries correctly. We can also use the host command to verify the name server. Send some DNS queries. As we can see in the output, the name server is translating queries correctly. It verifies the name server configuration. Now let's switch back to the server. Send a DNS query to translate a name into the IP address. Now send another query to translate an IP address into the name. As we can see here, the name server translates the name into the IP address, but it fails to translate the IP address into the name. This happens because so far, we configured only forward mapping that translates names into the IP address. If we want this name server to translate IP addresses into names, we need to configure reverse mapping. Before we configure reverse mapping, let's understand what the mapping is and how it works in the DNS system. In the DNS system, there are two types of mapping: forward mapping and reverse mapping. The DNS system was mainly designed for forward mapping. In forward mapping, name servers translate names into IP addresses. Later, they added reverse mapping to the DNS system for security and diagnostic purposes. In reverse mapping, name servers translate IP addresses into names. It is an optional feature. Although it is an optional feature, you should use it. In modern computer networks, many services use it to authenticate the source address. For example, email service uses it to verify the source email address. If you do not configure reverse mapping for a domain, other domains will not accept emails originating from it. In forward mapping, when an end device wants to know the IP address of a remote device or service, it sends a name resolution query to the resolver system. The resolver system forwards that query to all named servers in a sequence until it finds the answer. This sequence is known as the DNS namespace. In other words, a DNS namespace is a sequence of domain names arranged in a hierarchy. A domain name is a text label for the domain. In this hierarchy, the root domain stands at the top. It uses a null character as the label. You can write a resource name with or without its parent's domain name. If you write its name with parent domain names, it is called a fully qualified domain name. A fully qualified domain name uses dots to separate domain names. It starts with the resource's name and ends with the root domain's name. Since the root domain uses a null character as the name, it always ends with a dot. This is an example of a fully qualified domain name. In this name, FTP is the resource name. It is the child of the example domain. The example domain is the child of the COM domain. The COM domain is the child of the root domain. Each domain uses an authoritative name server to resolve queries for resources available inside it. If it has a child domain, it does not resolve queries for the child domain. It provides a referral to the child domain's authoritative name server. Only authoritative name servers can resolve queries. If a name server is not authoritative for a domain, it provides a referral to the next authoritative name server in the sequence. Since all authoritative name servers work in a hierarchy, a resolver system can easily reach the authoritative name server that can resolve its queries. This process is an example of forward mapping. In reverse mapping, a resolver system resolves an IP address with the name. Suppose the resolver system wants to know the name of the IP address 192.168.0.3. For this, it follows the same steps it uses in forward mapping. It sends the first query to the root name server and follows the referral until it gets the answer. Unlike fully qualified domain names, IP addresses do not include domain names. An IP address includes two types of addresses, the network address and the host address. For example, in the IP address 192.168.0.3, the network address is 192.168.0, and the host address is 3. Network addresses are used to organize and find IP addresses. Host addresses are used to provide a unique identity to an endpoint or a resource. A network address is like a domain name. A host address is similar to a resource name. Since IP addresses do not include domain names, developers used a different approach to build a domain tree for IP addresses in the DNS namespace. They created a domain called ARPA as a child domain of the root domain and used it to build a domain tree for IP addresses. There are two versions of IP addresses, IP4 and IP6. To keep the IP addresses of both versions separate, they created two additional domains as the child domains of the ARPA domain. For IP4 addresses, they created the in-address domain. For IP6 addresses, they created the IP6 domain. They constructed the domain tree for both versions inside their respective domains. To construct a domain tree for IP addresses, they used network addresses. But there was a problem. Unlike domain names which are written from right to left in fully qualified domain names, network addresses are written from left to right in IP addresses. To solve this problem, they flipped the IP addresses in the domain tree. For example, the IP address 192.168.0.3 will be written as 3.0.168.192 in the domain tree. The DNS system uses fully qualified domain names. A fully qualified domain name includes all parent domain names. To convert this address into the fully qualified domain address, we need to write its parent domain's name with it. 192.168.0.3 is an IP4 address. The parent domain of IP4 addresses is in address. The in-address domain is the child of the ARPA domain. The ARPA is the child domain of the root domain. Because of this, the fully qualified domain name of the IP address 192.168.0.3 will be 3.0.168.192.in-address ARPA. If the resolver system wants to know the name of the service or host using the IP address 192.168.0.3, it sends the first query to the root name server. The root name server provides a referral to the ARPA name server. The ARPA name server provides a referral to the in-address name server. The in-address name server provides a referral to the 0.168.192 name server. The 0.168.192 name server provides the name associated with host address 3. This process is an example of reverse mapping. Authoritative name servers use zone files for translation. There are two types of zone files, forward lookup zone file and reverse lookup zone file. A forward lookup zone file maps names with IP addresses. A reverse lookup zone file maps IP addresses with names. Forward lookup zone files are compulsory. You need to create a forward lookup zone file for every domain. In that file, you need to add records for all resources whose names you want to translate. Reverse lookup zone files are optional. You only need to create a reverse lookup zone file for the domain which runs services that need reverse mapping. In that file, you need to add records only for those services that need reverse mapping. If you do not want to provide reverse lookup for a domain, you do not need to create a reverse lookup zone file for it. There are two versions of IP addresses, IP4 and IP6. You can use a single forward lookup zone file to map names with IP addresses of both versions. But you cannot use a single reverse lookup zone file to map both versions' IP addresses with names. You need to use separate reverse lookup zone files for both versions. You only need to create a reverse lookup zone file for the IP version your domain uses. For example, if your domain does not use IPv6 addresses, you do not need to create a reverse lookup zone file for IPv6 addresses. A reverse lookup zone file uses the same configuration style as a forward lookup zone file. You can easily create a reverse lookup zone file from the forward lookup zone file. As mentioned earlier, a forward lookup zone file is compulsory for each domain. You need to create and configure it before you create and configure the reverse lookup zone file. If you have a forward lookup zone file, you can easily create a reverse lookup zone file from it. Let us understand this process through an example. Linux saves zone files in the /var/name directory. This is the forward lookup zone file of the example.com domain. Create a copy of this file. You can choose any name for the copied file. Usually, administrators prefer the domain's network ID with a DB extension. It makes finding and managing zone files easier. In our example, the network ID of the example domain is 192.168.0. Flip this address and add a DB extension to it. Open this file. This is a line comment. The name server will ignore it. Change it to indicate that this is a reverse lookup zone file. The next is the TTL directive. It defines the maximum time other named servers or resolver systems can cache records served from this file. Keep it as it is. The next is the origin directive. It defines the fully qualified domain name. As explained earlier, in reverse mapping, a fully qualified domain name is the complete network address of the domain. Specify the complete network address of the domain. Zone files are not case sensitive. You can specify a name in both upper and lower cases. The next is a start of authority record. It defines the characteristics and properties of the domain. The next are the NS records. These define authoritative named servers for this domain. The start of authority and NS are compulsory records. These records are the same in both the forward and reverse zone files. You do not need to make any changes to these records. Keep them as they are. Next are mail server records. We do not need them in the reverse lookup zone file. Remove these records. Next are the host records. In a reverse lookup zone file, we use the PTR record type for these records. Unlike forward mapping, reverse mapping is not compulsory. We do not need to add PTR records for all hosts. We need to add PTR records only for publicly accessible services such as mail, web, and FTP. Remove all host records whose names you do not want to make publicly visible. In the remaining records, change the resource record type to PTR. Now, we need to interchange the resource name and IP address fields values. While doing this, we need to take care of the zone file's automatic name conversion rule. Remember, in a zone file, if a name does not end with a dot, the zone file automatically converts it into a fully qualified domain name using the origin directive's value. We use this rule in the resource name field. In it, we specify only the host name and let the zone file convert it into a fully qualified domain name using the origin directive's value. Pick only the host addresses from IP addresses and place them in the resource name field. Because of the same rule, we need to convert these resource names into fully qualified domain names. If we do not do this, the zone file will automatically convert them into fully qualified domain names using the origin directive's value. For example, it will convert this name into this name. It will be an incorrect configuration. Convert all resource names into their fully qualified domain names. That's all we need to do in this file. Save the file. Now, this file is ready to translate IP addresses into names. To configure reverse mapping, we need to add a reverse zone configuration in the named conf file. Open this file. Go to the zone section. Create a new zone after the forward zone configuration. A reverse zone uses the same configuration a forward zone uses. Configure type option to master. Specify the zone file name. You need to create this file in the /var/name directory. Configure the value none in the allow transfer option. We will configure this option later. Save the file. Now we need to create the zone file for the reverse mapping. To create it, We can use the forward zone file as the template. Create a template from the forward zone file. For the reverse zone file, use the same name you configured in the reverse zone configuration. Open the file. You can update comments or can leave them as they are. Leave the time to leave directive as it. Update the origin directive. DNS will use this name to convert all relative names into fully qualified domain names. We do not need to update or change the start of the authority, name server, and mail exchanger records. Leave them as they are. Update the resource record type of host records. Now exchange the resource names and IP addresses. Use only the host portion of IP addresses. Do not add a dot at the end of the host addresses. DNS will automatically convert them into fully qualified domain names by adding the origin directive's value. We need to convert these names into fully qualified domain names manually. Add domain name with all names. Save the file. DNS will not read this file until we restart the name service. Restart the name service. Now send some DNS queries to translate IP addresses into names. As we can see here, now the DNS server is translating IP addresses into names. It verifies that the reverse mapping has been configured correctly. Now test it from the DNS client system. Perform the same tests from the client system. As we can see here, the name server is translating names into IP addresses and IP addresses into names. It verifies the name server is correctly configured to provide forward and reverse mapping. A slave or secondary name server fetches zone files from the primary or master name server. To configure a secondary or slave name server, first, we need to configure the primary or master name server to transfer zone files to the secondary or slave name server. On the master name server, open the name.conf file. Go to the zone section. Configure the allow transfer option in both zones. Remove the value none and add the secondary or slave name server's IP address in this option. Save the file. Restart the name service. Now go to the system you want to use as a secondary or slave name server. Open the /etc/name.conf file. Configure the listen on port 53 and the allow query options. Go to the zone section. Here we need to add two zone configurations, one for the forward mapping and another for the reverse mapping. In both zones, configure the type options value to slave. DNS saves the files it receives from the master name server in the slave directory. The third option is masters. DNS automatically sends zone transfer requests to the name servers specified in this option. Configure the primary name server's IP address in this option. By following the same steps, you can configure the reverse lookup zone. The reverse mapping is optional. Because of this, you need to configure a reverse zone here only if you configured the reverse mapping on the primary name server. Save the file. Go to the /var/name/slaves directory and list the content. As we can see here, at this time, this directory has no zone configuration files. The name server will not read the new zone configuration until we restart the name service. Restart the name service. Now list the content again. The name server automatically fetched these zone files from the master name server. This name server will use these zone files to resolve DNS queries when the primary name server fails. It will work as a backup name server for the primary name server. DNS clients know nothing about this name server. We need to update their IP configuration to use this name server as a backup name server. Open the IP configuration on the client system. Add the backup name server's IP address. Restart the connection. Verify the updated IP configuration. Now send a DNS query and check the name server's IP address in the output. As we can see here, this query has been resolved by the primary name server. Now go to the primary name server and stop the named service. Now send another DNS query and check the name server's IP address in the output. As we can see here, this time, the query has been resolved by the backup name server. It verifies the secondary or backup name server configuration. The backup name server will resolve queries only until the primary name server remains down. As soon as the primary name server comes online again, the client system will stop using the secondary name server. To verify it, start the name service on the primary name server. Now test from the client system again. As we can see here, this time, the query has been resolved by the primary name server. It verifies the secondary name server translates DNS queries when the primary name server is down. That's all for this video. If you have any suggestions, comments, or feedback about this video, please share them with us in the comment section given below.